Assalamualaikum warahmatullahi wabarakatuh and hi everyone. So we meet again. This week we will continue to the new topic about control system engineering, which is controller design. So first, let us look at the learning outcome for this topic. So at the end of this lecture, you should be able to know the importance of controller for the system and why we need to design the controller. Second, familiar with the terms proportional gain, integral gain, and derivative gain. Next, you should be able to design the controller to improve either transient or steady state performance. So that's mean based on the performance that we get from the original system. So we improve if the performance is not good. So either we improve transient part or steady state part. So next, you should be able to differentiate between ideal and non-ideal compensator. Compensator mean controller. So after you design the controller, so you can implement that controller either using passive or active circuit that we call ideal and non-ideal compensator. Okay, so we start with introduction. The root locus that you have learned before typically allows us to choose the proper root gain to meet transient response specification. So why we need to design the controller? So we need to design the controller because of two objectives. Number one, we want to improve the transient response. As you can see in this response, so the blue one is the input, and that what we give to the system or our target for the system. So that's mean we want the system follow this step input. So the red one is the output for the system. So based on this output of the system, and based on this response, this part, the starting point before the system become steady state, we call transient response. Okay. Next part, and this part after system become steady, we call steady state part. Based on this response, this is what you have learned in the previous lecture. And based on this response, so we can know the overshoot of the system, TS, TP, and so on. So that one is a parameter for transient response. And also based on this response, we can know the steady state error. Okay, steady state error is a parameter for steady state condition. So this is why we have to design the controller because of these two objectives. So that means we want to improve. For example, this one, the overshoot of the response is quite big. So we want to reduce this overshoot. We can design the controller to improve this part. And also for this one, so as you can see here, there is an error for the system because there is a little bit difference from the blue one and the red one from the input and the output response. So these are different. We call the steady state error. So in order to improve this one and to eliminate this error, we have to design the controller. In order to improve the transient response, so we can add differentiation. Okay. So what is differentiation? I will show you later on. Next, to improve the steady state error at this part, so we can use integration in the forward part. So what is integration? I will show you later on. In order to design the controller, we can choose either this configuration or this configuration. So this configuration we call cascade configuration, where we put compensator in front of this original controller and plant. So plant in this case represent system that we want to control. Okay, this is what we call cascade compensator. For feedback compensator, we put another controller at feedback part. This is the original controller that I already have for the system, and we put another feedback control at the feedback part So this one we call feedback compensator. Compensator type. So basically we have two type of compensator, which are ideal compensator and non-ideal compensator. Ideal compensator use pure integrations or pure differentiation. So this kind of compensator can be implemented with active network circuit. Active circuit means circuit that include component that deal with power supply. Advantage of this ideal compensator is this type of compensator can improve steady state error, which is can eliminate the error so that the steady state error become zero. While the disadvantage of this kind of compensator, it require additional power source for their operational. For non-ideal compensator, this kind of compensator we can implement only based on passive element. Passive elements in this case mean we use basic component in electronic, that is resistor, capacitor, and inductor. So for active network, we use operational amplifier. Okay, advantage for this kind of compensator and this non-ideal compensator is less expensive and very cheap. You just imagine how much we just pay for resistor, capacitor, and inductor. So very cheap and do not require additional power source for their operation. That's mean in order to operate that circuit, there is no power source needed. However, the disadvantage of this kind of compensator, the steady state error is not driven to zero. So that means we just only can reduce the error, but cannot eliminate that error. Proportional gain. So what is proportional gain? So the proportional gain is the most important tuning parameter. Basically, we need this proportional gain for closed loop system. So it affects the responsiveness of the system. A low gain makes the system sluggish and unresponsive. So the proportional gain is usually a fixed property of the controller, but in some proportional controllers, K is manually adjustable. So if K is increased, the sensitivity of the controller to error is increased, but the stability is impaired. The system approach the behavior of on-off control system and its response become oscillatory. Proportional control does not incorporate the time that the error has existed. There will always be an offset from set point. Now let us look at how to improve the steady state error without appreciably affecting the transient response. So there are two ways to improve the steady state error for the feedback control system using cascade composition. First, we can use ideal integral, and second, we can use non-ideal integral. For ideal integral, we just combine integral equation with proportional equation that we call proportional plus integral PI controller. The idea is we add another pole at origin, and because when pole at origin, system become type 1. So when system type 1 for position control, the error become 0. So please recall back what you have learned in the previous control fundamental that you have learned in the previous semester. For non-ideal integrals, we can eliminate the error, but we can reduce the error. So that means error almost to zero. So in order to do that, we just pole and zero close to each other. That pole and zero should be close to the origin. So this one we call lag compensator. This PI controller is active controller. So this lag compensator is passive controller. So in order to implement this PI controller, we have to use circuit that involved with operational amplifier. For this lag compensator, only involve RLC circuit. For ideal integral compensation PI controller, the design should improve the steady state error without appreciably affecting the transient response. So this is because we want to remain the performance of the system in terms of transient response. So the following equation represent the transfer function for PI controller, where GPI means transfer function for PI controller in S domain equal to K is gain, times with S plus ZC divided by S. Okay, as you can see in this equation, so we put integrator is 1 over S. So based on this equation, okay, that means we just put one pole at the origin, and then we put another zeros close to the origin, so that it can remain the performance in terms of transients. To be more clear about this, let us look at this figure. This is the block diagram that represents the system that we have discussed. For the system with three pole, the number of branch is 3. So that means we have the direction for root locus, the direction for pole when k is increased based on 3 root. This is root number 1, this one is root number 2, and this one is root number 3. So when we put another pole at the origins, so the branch for the system become 4 because we have 4 pole. So the direction for the root for pole become like this. These two pole will follow this route, and the other two pole will follow this route. We can get this root locus by using the rules that you have learned in the previous lecture. When the root locus for the system change, so that means the performance of the system in terms of transient response also change. So in order to remain that transient response performance, so we have to add another zeros here that is close to this pole, where when k is increased, this pole and zero will cancel each other. So that means with certain value of k, the root locus for the system come back to the original root locus has the original system without PI controller. That is how we can improve the performance in terms of steady state without affecting transient performance. Okay, now let us look at this example. For example, we have a system with negative unity feedback with GS equal to K divided by S plus 1 times S plus 2 times S plus 10. This one. Design the controller so that its steady state error for a step response is reduced to 0. That means we have to design PI controller because we want to eliminate the error. With damping ratio zeta equal to 0.70. So in order to solve this problem, first we have to find the location of pole when zeta is equal to 0.707. Okay, to find that, we have to use this formula where zeta is equal to cos theta, and from there we can find the value for this theta. This theta is represent theta angle start from real axis to this location of pole when zeta equal to 0.707. So based on this calculation, we get theta equal to 45. We just draw the line and start from origin with angle 45 degree like this. The crossing point between this zeta line and this root locus represent the location of pole when zeta equal to 0.707. From this location of poles, so we can find the value for this k. Whereas in this case, we just put the location of pole, which is negative 1.37 plus J 1.4. So we just use this formula based on this GS. So after we apply this formula, we get K equal to S plus 1 times S plus 2 plus times S plus 10, where S is equal to negative 1.37 plus J 1.4. So after we solve this, we get K equal to 19.32. Okay, after we know this value of K, we just apply this formula, and because we want to eliminate the error, so first we have to check the steady state error for the uncomposite system. That means steady state error system without controller. So in order to check the steady state error, we just use this formula Kp equal to limit S to 0 Kgs. Okay, this is the formula that you have learned in the previous control system fundamental. So please recall back. So we just substitute this GS in this equation. So Kp is equal to limit 19.32 is value of K divided by S plus 1 times S plus 2 times S plus 10. So we just substitute this S equal to 0 in this equation, and then we get the result is equal to 0.966. Okay, after we get this value of Kp, we can calculate the steady state error by using this formula, where the steady state error is equal to 1 over 1 plus Kp. We just substitute this value of Kp here, and then we get ESS for this system when location of pole at this point is equal to 0.5086. Okay, this is the steady state error for the system without compensator, without controller. So now our objective, we want to eliminate this error so that the error become 0. In order to do that, so we have to design the PI controller. The general transfer function for PI controller is GCS, this one, GCS equal to K1 plus K2 divided by S. We can rearrange this equation become like this. So K1 times S plus K2 divided by K1 divided by S. Okay, this equation same like the previous equation that I showed to you, this one, GPI equal to K S plus ZC divided by S, where ZC in this case is equal to K divided by 1. Okay, let K1 equal to 1 and K2 equal to 0.1 to ensure it is close enough to the pole at the origin. Okay, because we want to design the PI controller, so first we have to put one pole at the origin, and then next we have to put 0 close to that pole at the origin. So that's why we choose K1 here is equal to 1 and K2 here is equal to 0.01. This is up to you. You can choose other value. For example, you want to choose 0.02 also can, or you want to choose 0.005 also can. It's up to you. As long as this value after we put in this equation close to 0. Thus, the transfer function for PI controller is given by GC equal to S plus K2 divided by K1. In this case, K2 is 0.01 divided by 1. So equal to 0.01 divided by S. So from there, the PI controller transfer function is equal to S plus 0.01 divided by S. So we just cascade with the system. So the equation, the transfer function for the whole system become like this: K times S plus 0.01 divided by S times S plus 1 times S plus 2 times S plus 10. So after we put this PI controller, so you can see that our system now is system type 1, and before our system is system type 0. So when there is one port at the origin, system becomes system type 1. Okay, for system type 1, and when we use this formula, and when we put S equal to 0 here, and then because here we have S in front of this equation, so that means this equation become infinity. So when this one become infinity, so when we substitute infinity into this equation, the result for ESS become 0. Based on this equation, we can implement the ideal integral compensator as indicated in this figure. So this is the structure for PI controller, where we have integral here, and this one is proportional gain. We combine together at summing junction here. So that means we add this one and this one, which is represent this equation. All this we call PI controller. In order to realize this ideal integral compensator, we can refer to this table. So where this is the standard circuit for PI controller. Based on our design, the value of Z1, Z2 can be obtained based on this equation, where we compare this equation with this derivation, and we just compare, and then from there we can find the value of R1, R2, R C, and so on. This is how we can transform to the real implementation. Okay, now let us look at another type of compensator or controller that we can use to reduce the steady state error. So the compensator name is lag compensator. For lag compensator, in order to design this compensator, we have to add one pole and one zero to the system. This figure illustrates how we can design lag compensator. So first we have to put this pole close to the origin, and second we have to put this zero close to this pole. So the purpose we put this pole close to the origin because we want the steady state error for the system almost zero. And then in order to make sure there is no change in the transient response, so we have to put this zero close to this pole. Okay, so let us look at the same example like PI controller. So we use the same result from the root locus here with three pole. And then when we add this lag compensator like this, we add pole close to this origin and we add zeros close to this pole. So we can see that when k is increased, this pole and this zero will cancel each other. The location of pole with this controller, as you can see here, look like same like before we put the controller. So this is how we can remain the performance in terms of transient response. So the procedure to design the lag compensator, so we start with determine the static error constant for the uncompensated system. So for uncompensated system, we just assume this closed loop system with gain k here. Okay. So when we put the controller, so the compensator become like this: k s plus zc over s plus pc. So static error constant for this uncompensated system, and this one we call uncompensated system, and that's mean without this lag compensator. In order to find the static error constant, we can use this formula where k z1 z2 divided by p1 p2. For the system with compensator, we also have to find the static error constant that we call static error constant for the compensated system. So the formula is same like here, but for this one we have to put ZC and PC in this equation. So the improvement in the compensator system, KV over the uncompensated system, KV is based on this relationship. So KVN equal to KVO, ZPC divided by PC greater than KVO. In order to keep the transient response unchanged, so the compensator pole and zeros must be close to each other, and like I mentioned just now. The ratio of ZC and PC can be large in order to yield an appreciable improvement in steady state error. There also will be a minimal effect upon the transient response if the pole zero pair of the compensator is placed close to the origins. So for example, the ratio of ZC to PC can be equal to 10 if the pole is at 0.001 and the zero is at 0.01, thus the ratio is 10. Yet the pole and zero are very close and the angular contribution to the compensator is small. Now let us look at another example, which is example about this lag compensator. We still use the same system like PI controller, which is GS equal to K divided by S plus 1, S plus 2 times S plus 10. But in this time, we want to design a lag compensator to improve the steady state error by a factor of 10. So that means we want to improve steady state error 10 times. And we want to make sure the transient response for the system is remain, which is at damping ratio 0.172. So in order to solve this problem, first we have to identify the location of pole when damping ratio is 0.172. So how we can get this location of poles, or we call dominant poles? So we can use the same as in PI controller. This one, the same procedure where we use this formula zeta equal to cos theta, and From there, we can get the value for theta, where theta is equal to inverse cos zeta. Only the difference is zeta, because based on that question, so we have to maintain the zeta equal to 0.1, maintain at 0.172. So we just put that value in this zeta, and then after we calculate, we can get the theta, and then based on that theta that we get, we just plot the line for this zeta. So this is the value for zeta that we calculate. The crossing point with this root locus, this one is a dominant pole for the system. So in this case, we get the dominant pole is equal to negative 0.692 plus minus because when pole add complex part, there is conjugate. So that's why we have plus minus here. So negative 0.692 plus minus J 3.93. Okay, next after that we have to find the value of this K. So also we use the same step as in PI controller. After we get that dominant poles, we just use this formula and then put that pole inside this S, and after that you just solve the equation and get the value for K, in this case equal to 165. Okay, next step, in order to improve the steady state error, so first we have to know the current steady state error. That means we just use the formula to find the error. So first we start with Kp equal to limit S to 0, Kgs. So we just put this equation inside this formula, Gs here. Then we substitute the value of this K that we have calculated to this equation here. And then we substitute all as in this equation with 0. And after we solve, we get Kp is equal to 8.25. Okay, based on this value of Kp, we just use the formula ESS equal to 1 over 1 plus Kp. And then we get the ESS for the uncomposite system is 0.108. So to get back to this question, the question asks you to improve the steady state error by a factor of 10. So that's mean after we design the controller, our steady state error should be 0.0180. And because we improve by a factor of 10, so we have to divide this with 10. And that's why we get 0.0108. So how we can design so that we can get that ESS equal to 0.08? So based on steady state error equation, this one, ESS equal to 1 over 1 plus Kp. So from here, we can rearrange this equation, become like this, Kp equal to 1 minus ESS divided by ESS. In order to make sure the ESS improve by a factor of 10, and that's mean equal to 0.0108. So we have to find the new value for Kp. So we just apply this formula to find a new value for Kp. We just put the value of ESS after composite like this, and then we get Kp new is equal to 91.59. The improvement in Kp from the uncomposite system to the composite system is the required ratio of compensator ratio to the compensator pole. Okay, so that means after we obtain this Kp new, so we just apply this formula. So we just put the value for Kp new 91.25, and also the old new for Kp 8.25 equal to ZPC divided by PC. So this value Kp new divided by Kp. So because we already know the value for Kp new and Kp for the whole value of Kp, so we just solve and then we get 11.06. So based on that, we can find the value for ZC and PC. So in order to make sure we can improve the steady state error, so we have to put the value for PC close to the origin. So in this case, I choose 0.01. This is up to you. If you want to choose 0.02 is also can. If you want to choose 0.002 is also can. It's up to you. As long as this PC should be close to the origin. And then we apply this formula, the value for ZC equal to 11.06, and this one refer to this ratio between KP new and KP old times PC. So PC we choose by ourselves. We just put PC here 0.01 and then we get ZC equal to 0.111. Transfer function for lag compensator that we have designed is GC equal to S plus ZC. ZC here is 0.111 divided by S plus PC. PC we choose 0.01. And then we just cascade with the plan, and the overall transfer function become GC GS equal to K times S plus 0.111 divided by S plus 0.01 times S plus 1 times S plus 2 times S plus 10. So after we get the transfer function for the lag compensator, we can implement by using this circuit. And this is the equation that represent this circuit. The arrangement for this equation is same like arrangement for lag compensator. In order to complete this circuit, we just compare this component with the value that we get from the transfer function for lag compensator, which is the same procedure like PI controller. Okay, that's all for today. So hope you can understand. Please do exercise that I attach in ULearn. If you have a problem, you can discuss with your friend. If you still not solve that problem, you can ask me. With that, Assalamualaikum warahmatullahi wabarakatuh, and thank you.